In this here velocity graph, acceleration is constant from critical point to critical point. This is generally the case for the problems in this class, that acceleration over any interval will be constant within that interval. So that means the acceleration between these 2 points is constant, and the acceleration between these 2 points is constant, and the acceleration between these 2 points is constant. Now the acceleration in this section might be different from this section and from this section, but it's always going to be constant in each section. Now one thing that's kind of cool about constant acceleration is that when acceleration is constant, average velocity equals initial velocity plus final velocity divided by 2. So what this means is that if we have some velocity and some other velocity, the average velocity in here between these two is going to be both of these divided by 2. And it's going to occur at a time that's exactly between the times of the other two velocities. And we can keep repeating this process, and what we end up with is that when acceleration is constant, a change in velocity is always represented by a straight line with a slope on a velocity graph. That slope can also be flat. 0 is a constant acceleration, and velocity can just remain the same as long as acceleration is 0. But before I even use that, I'll focus on another concept, which is even easier, which is that here we have position and there we have time, and velocity is change in position divided by time. That's actually average velocity, but again, average velocity is going to be between the 2 points is going to be, there's something in there that I'm not specifying quite clearly, but I'm going to try to complete this document more quickly, and if you'd like, ask me further questions in class. Okay, so from here to here, the change in velocity between these 2 points is 0. And over a second, change in 0 over a second is going to be 0 meters per second. And that's going to be the same everywhere between these 2 points. So that means that over here from 0 seconds to 1 second, let me and I'd recommend probably doing these in pencil first. From between 0 and 1 second, our velocity is 0 because that's the slope of the line at all the points between those first 2 red dots. Now from here to here, it's going to be a little bit tricky. That's where we'll use that rule that we were talking about here with average velocity. But for now, let's skip ahead to this other place where we have a constant continuous change in position. So since the velocity is the slope of this line, and the slope of a line is always the same along a line, all we need to do is find the slope of the line to know the velocity from 2 seconds to 5 seconds. So again, we're looking for from 2 to 5. So So right now I'm going to skip the part from 1 to 2 seconds. And at the end of this you'll kind of see why. And this slope, again, slope is always rise over run. So we have here a rise of negative 1/2 plus 1 plus 2. Okay, negative 1/2 plus minus 1 minus 1 again. So that's negative 2.5 minus another half. So a rise of negative 3 over 1, 2, 3 seconds. So negative 3 meters divided by 3 seconds is going to be a velocity of negative 1 meters per second. So that's going to go right here. That's kind of hard to see, but that's a negative 1. It almost looks like it could be a sideways 1. That's just how the camera is. But that's negative 1 meters per second. Again, that velocity is constant for that whole interval. And then again, we'll skip this curved portion and then look at the time between 6 and 7 seconds. And there's no rise at all between those 2 points. So the rise over the run, since the run is a second, 0 divided by 1 is 0. So from 6 to 7 seconds, again we have a a velocity of 0. Oops. See, I should have used a pencil here. We have a velocity of 0 meters per second. There's faulty data. And then I'll skip this next curve, and at 9 seconds we get another straight line. So again, I just need to take the slope of this, and it goes over to here where I get a ½ second, but I'm just going to look at this kind of rectangle here that's between grid points, so it's easier to count. Rise of 2, a run of 1 second, so 2 meters divided by a second is going to be 2 meters per second, and that's for the time from 9 to 10.5 seconds. So for that period, from 9 to 10.5 seconds, we had 2 meters per second. So from 9 to 10.5, we have a velocity of 2 meters per second. And then again, I'll skip this curve here, and then after that we get another portion where there's no rise over the run. So after that, oops. Okay. So that goes from, looks like 11.5 seconds onwards. So after 11.5 seconds, we again have another slope of 0 meters per second. So our velocity is 0 meters per second for that interval. Okay, so now we'll focus kind of on the in-between points. And because we know that from the effect of constant acceleration that the velocity, that changes in velocity under constant acceleration will form a straight line on a velocity graph, that means that all those in between intervals we can just connect the lines. So I'll just do that now. And as you see, during this curve, velocity is decreasing. It goes from 0 to -1 meter per second, which is what we get there. And then in this curve, it's rising. Again, at the same rate. About. And then from here to here, it's also rising, and again, the slope of the velocity line seems to be the same in these first cases. And then from this last portion we get another decrease, but it's about twice as steep as the others. So that means that during this last point, it's like the train was hitting its brakes and stopped a little bit faster than its change in acceleration was more extreme than its others. So the magnitude of this change in acceleration would be the greatest. Even though it's negative, the magnitude is the absolute value. So the magnitude of the acceleration here is going to be the slope, which is will be the absolute value. The slope here is a run of -1, -2, so -2 meters per second over 1 second, which is -2 meters per second. But the magnitude of that is going to be 2 meters per second. So, and that's greater than any of the others, which are all 1s or 0s. So now the acceleration graph, we do exactly what we did between the position graph and the velocity graph, yet since acceleration is always constant between intervals, it's always going to be a flat line. And that flat line between points is going to be the slope. So from 0 to 1, the slope is 0. So that means from 0 to 1 second here, the velocity, the acceleration was 0 meters per second squared. So acceleration is meters per second squared. And here we have time. And you could continue this, well, this step graph doesn't really have any continuous changes in acceleration, so we can't really, another graph would just be 0. With some undefinable points, but that's not anything we need to get into. So for the next second, we go from 0 to -1 meters per second over a second. So that's -1 meters per second squared is the rise over the run. So again, we have another flat line, but it's at -1 meters per second. And then again, here we have an interval where the rise is 0 over a run of 3 seconds. So for these 3 seconds, the acceleration is 0 meters per second. We're not really going to worry about what happens from here to here. And over here the slope has a rise of 1 goes from -1 to 0, so 0 minus -1 is +1. Divided by 1 second is 1 meter per second positive. So this is a negative acceleration, which we see here, and this is a positive acceleration. And notice that everywhere where there's a line so far, the acceleration is 0. So wherever you see a line, so far the acceleration has been 0, because the velocity doesn't change when the position graph is a straight line. And if velocity doesn't change, no matter how fast something is going, the acceleration is 0 if velocity is constant. So I'll just finish up the next several intervals. Get another one after I suddenly apply that one of from here to here of +1 meters per second, and then from there to there a rise of 0, so no change in velocity. So again, 0 meters per second, and it's also if we look up at the position graph, it's a straight line there. And then this next section, it has a rise of 2 over a run of 2, so 2 meters per second divided by 1 second gives us 1 meter per second, and that's over a 2-second period. And then finally, almost there, we get another point where rise and run is 0. So from 9 to 10.5 seconds, we have another portion with 0 meters per second as per second squared as the acceleration. And then here we have that really steep slope, which goes minus from 2 meters per second to 0 meters per second, and 0 is the final velocity, minus 2 is initial velocity, is -2 meters per second divided by an interval of 1 second, and that gives us from 10.5 to 11.5 seconds, -2 meters per second squared. And even though this is negative, its magnitude doesn't have a direction, so the magnitude is going to be positive. So it's going to have, so even though this is the lowest point on the graph, it has the acceleration here is greater than at any other point, the magnitude of the acceleration. It's just that it's going in the negative direction rather than the positive direction. And then again we have another flat line with the rise of 0 over a run that continues off the graph, starting at 11.5 seconds and going onwards. So seems that everywhere we had a flat line, like even here where the line is going up, when we trace it down, we have a constant velocity. It's a high velocity, it's at 2 meters per second, but it's still constant, no change in velocity over that time. And so we get to our acceleration graph, it's along the 0 meters per second acceleration. So everywhere where there's a flat line, the acceleration is 0 meters per second, no matter what the slope of that line is. So position can be changing a lot. Velocity can be kind of high or low or 0. And in any of those cases, as long as the velocity isn't changing in that interval, it's flat. If the velocity is changing, then the velocity is going to be the slope of the velocity graph. So that's how we go from position to velocity to acceleration. With that, enjoy physics.